Hello and welcome back to our lecture videos. This is week 13, chapter 7, part 1. And chapter 7 isn't very long as far as homework and things like that go, but I'm going to be breaking it up into a couple of different sets. So the title of chapter 7 is Atomic Structure and Periodicity, but I like to think of it as a quantum mechanics introduction. So it's got some interesting stuff in it. There's not a ton of math in it. So for people who don't love the math, that could be good news. But there's a bunch of other things that need to be understood. Okay. So first of all, we're going to begin by talking about electromagnetic radiation. Okay, and also sometimes called EM for electromagnetic. Okay, and there are three main, well, actually first, before I do anything, let me go ahead and stop this share and let's share one of the slides. So if you've watched the slides, you've probably seen this. And hopefully you can see this on the screen. These are our classifications of electromagnetic radiation, okay? And it goes down here from gamma rays up to radio waves even, okay? And the main thing with electromagnetic radiation is that it travels at the speed of light in a vacuum. Okay, so it might be different, when you're dealing with, atmosphere and things like that, but not so much. So let's go ahead and take a look at a couple things here. First of all, okay, down here on the end, you'll see that it says gamma rays, okay? And the gamma rays, you'll see this little 10 to the negative 12th. That means that the wavelength for a gamma ray is about, okay, so there's only one significant figure here. It's about, and there's a range, of course, is about 1 times 10 to the negative 12th meters. Okay. And now we'll come over here and you'll see over here we have radio waves, okay? And the wavelength of radio waves really depends, okay? So we'll say the wavelength of radio waves is about, and again, it changes based on what we're working with there, 1 times 10 to the 4th meters. And here in the center, right here, you can see this lovely rainbow of color. This right here is our visible light spectrum. And that's what we can see, okay? And here, down here, it talks about, it says here we talk about the wavelength of visible light occurring from 4 times 10 to the negative 7th to 7 times 10 to the negative 7th meters. But we talk about visible light so often that we don't tend to talk about it in terms of meters. So we have to be able to do the calculations in meters, but we talk about it in terms of nanometers. Okay, so let's do a quick review about that conversion. So first of all, there are 1 times 10 to the 9th nanometers in 1 meter. Okay, so let's say that we're looking right here. I have that 6 times 10 to the negative 7th. Okay, well, what would that be in nanometers? Well, 6 times 10 to the negative 7th meters, okay, times, okay, so we have to have meters on the bottom so that they'll cancel, and the nanometers on the top, and then we put in that 1 times 10 to the 9th nanometers over 1 meter. Go ahead and check your calculator if you're not sure. But when you do this 6 times 10 to the negative 7th times 1 times 10 to the 9th, you will get 600 nanometers. And that is the wavelength of this color light right here. Okay, all right. Okay, now let's go ahead and go back to our whiteboard. And we're going to talk about what some of those things mean. So when we're talking about electromagnetic radiation, we saw all the different things that make up the EM spectrum. There are 3 key points that we're going to be looking at, and one is wavelength. And the symbol for wavelength is a Greek character called lambda, and it looks like this. This little funny symbol here is the Greek character lambda, and it means wavelength. And the wavelength is how, is the distance. Let me go ahead and show a little bit here. So let's imagine that we have an interval, and this interval occurs in 1 second. Okay, and in this interval we have there we go. Okay, we have these waves. All right, so what is lambda? Okay, lambda is this distance here. Okay, it's the amount of space from peak to peak or trough to trough. Okay, now the next thing that we have is we have frequency. Now frequency is the symbol for frequency is nu. Okay, and nu is for frequency is the number of cycles per second. So here we have 1, 2, 3. See, and this part could be over here. Okay, so we have 3 peaks, 3 troughs. So the frequency for this is 3 cycles per second. A cycle per second can also be shown as S-1, seconds -1. We don't really refer to the seconds, or as hertz. Okay, and the wavelength here, when we do our calculations, this wavelength needs to be in meters, as we saw before. And now the piece that ties this all together is speed. And again, electromagnetic radiation travels at the speed of light in a vacuum. Therefore, speed, or C, is going to be the speed of light in a vacuum. And you're going to be using 2.9979 times 10 to the 8th meters per second. And the equation that ties this all together is that C is equal to lambda nu. And if you're not feeling real up to the algebra for this, that means that you could solve for lambda by saying C over nu, or the speed of light divided by the frequency. And you can also solve for frequency, or solve for nu, by saying C over lambda. Okay, so that's the equation that we'll be using for that. Okay, so now let's go ahead and take a look at what some of that math might be. So let's look at the problem. Find the frequency of red light at 650, and actually, hang on a second. I want to give myself 3 significant figures here. So 652 nanometers. Okay. Well, our step 1 for this is to convert to meters. Okay, so we take that 652 nanometers and we multiply it by 1 meter over 1 times 10 to the 9th nanometers, okay, which means really that we're dividing 652 divided by 1 times 10 to the 9th nanometers. And this will become 6.52 times 10 to the negative 7th meters. And this is our wavelength. Right, and now our step 2 is to find frequency. And we'll do that by using the formula that I gave you on the previous slide. That says that frequency, or nu, is equal to the speed of light, c, divided by the wavelength. So we have 2.9979 times 10 to the 8th meters per second divided by 6.52 times 10 to the negative 7th meters. And now if you're curious about the units, that cancels our meters and we're left with these inverse seconds. And now I pull out my calculator. You should pull out your calculator too, because it's been a while since you've used all this big scientific notation and you want to make sure before the test that you're doing it correctly. 2.9978, and I have an EE button, 8 divided by 6.52 times 10 to the negative 7th. Now, when you put that in your calculator, what you should get, okay, we can have 3 significant figures. So I'm getting 4.598006 times 10 to the 14th. But I can only have 3 significant figures. So the way we do this with 3 significant figures is 4.60, because the 8 will round this up, times 10 to the 14th hertz. And that's because that seconds negative 1 is a hertz. Okay. All right. Let me take a look at what we got here. Okay, now the next piece, let's go ahead and continue this same equation. All right, so moving on, what we'll have is we can also determine the amount of energy in one of these photons. So Einstein proposed that energy is quantized, and this is in your annotations in your slides, so I want you to read that. But let's go ahead and take a look at continuing this, and we'll say, what is the energy of our photon? And this is the photon that we've just been working with here, okay? So this is the frequency of, we'll call this a photon of red light. So the frequency of a photon of red light at 652 nanometers. Okay, so now let's continue this, and what we're going to use for that is we're going to learn that the energy of a photon is equal to h nu, or hc over lambda. So you can either do this from nu, which is right here, or you can calculate this directly from lambda up here, either one of these 2 equations, okay? And what we'll be using then is that h, Planck's constant, and this is all in your notes, of course, but h, or Planck's constant, is 6.626 times 10 to the negative 34th joule seconds, okay? And that will give us an energy of our photon in joules. Okay, so let's go ahead and find this. So we put in Planck's constant, 6.626 times 10 to the negative 34 joule seconds, okay, times, now we could do C over lambda, or since we've already calculated nu, we'll just go ahead and use that, 4.60 times 10 to the 14th. And I'm going to change this hertz to inverse seconds so that we can see how our units cancel. So seconds and inverse seconds cancel, and we're left with just joules. Okay, and then again, pulling out my calculator, 6.626 times 10 to the negative 34th times 4.6 times 10 to the 14th. And the answer that I get for that is, and I can have 3 significant figures just because of my 3 sig figs here. And so I get 3.05 times 10 to the negative 19 joules. So it's very small. If you remember all those values we were getting chapter 6, you'll think, oh, wow, this is really, really tiny. And it is very small. Okay. So I'm just looking at my notes to see what's next. Okay, so the next thing that I'm going to do, I'm only going to do some of chapter 7 in this video, mainly so that you just have it in a couple of different sections. Okay, and again, don't forget to read over and take notes on the annotations and the slides as well, because this is just meant to supplement that. The next thing that we're going to do here is we're going to talk about quantum numbers. And again, read about orbitals and things like that. That'll be very important. And you'll be answering questions about it in your tests and stuff. But now what we're going to do today is we're going to look at quantum numbers. And the quantum numbers are basically, it's kind of like the special address that each electron in an atom has. Okay. And so what we mean by that is that, let me see where we're at. There we are. Okay. What we mean by that is each one will be kind of separate. Okay. So when we think of an atom, you know that like hydrogen has 1 electron. And then if I look at my periodic table here, I could go over to iodine and I could see that it has 53 electrons. And I could go all the way down to erbium, ER number 68. That one has 68 electrons, right? So we can keep going down the periodic table and we can see 1 electron all the way up to all these. And the thing is that where are they? And the electrons aren't just cast anywhere within the atom, they're in this electron cloud. And we can sort of predict where we're most likely to find them. And that's what that probability is of an orbital. So an orbital is the place, the 3-dimensional place or space that we are likely to find the electron about 90% of the time. And we describe that space using a set of 4 quantum numbers. The first one is the principal quantum number. Actually, and I'm going to make my life a little easier here. And we're just going to change that principal quantum number. There we go. The principal quantum number is called n. And n can be a variety of, well, first of all, before we get there, n is the size. So the size and the direction, the distance from the nucleus of our energy levels. Okay, so it's the size and energy level of the orbital that we're in. And n can be integers. It can be 1, 2, 3, 4. So the smallest, the first n level is 1, and so on and so forth. Okay, hang on a second now. We're going to go find Sorry about this. You're all looking and I'm looking on my, there we go. Okay. All right, so here we are at the periodic table. So let's go ahead. I'm going to come back and forth between these. Okay, and this is the periodic table that you guys are used to seeing. Okay, now we said energy level 1, 2, 3, 4, and so on and so forth. Well, we describe our energy level by the row that we are on the periodic table. So this will be n is equal to 1. This row will be n is equal to 2. This row will be n is equal to 3, 4, 5, 6, and 7. Now, that's true also over here as well. So hopefully you can see this. I know that there's things on your screen, but helium is also energy level 1. But now over here, starting with boron, this is also energy level 2, 3, 4, 5, 6, and 7. Okay. And so energy level 2 encompasses lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Now things get a little bit tricky because scandium, our first transition metal here, is not an energy level 4, it's an energy level 3. And I'll explain why probably next week. And then yttrium is in energy level 4. So you'll see that we're just kind of coming down from here like this. See? And lutetium is in energy level 5 and lawrencium in energy level 6. Okay. Now, I wonder if I can. Sorry. Okay. So if we were to stop annotating just for a moment. And I know that this is really hard to see. If we were to come down here, lanthanides are you know what, I'll do the lanthanides and the actinides in a minute. The annotations don't stay where I put them. Okay, so let's come back now and to our whiteboard. Okay, so those are our principal quantum numbers, or N. The next of the quantum numbers is the angular momentum quantum number. And the angular momentum quantum number is depicted by a lowercase cursive L. And that's kind of weird, but you'll see it like this. And that's kind of like I say, that's a lowercase cursive L. And I'll circle that in red so that we can see it. And this angular momentum quantum number, so here we indicate the size and energy level of our orbital, 1, 2, 3, 4, 5, and so on. Okay, this one indicates the shape of our orbital. And it depends, it's the shape of our orbital, and it's sometimes called a subshell. And N is usually called a shell. I'll put that here. I've forgotten to say it before. Okay. Now, L depends on N. So if N, actually, L depends on N. Let me go ahead and show that. L is equal to 0 to N minus 1. What does that mean? Okay, that means that if N is equal to 1, we have one L value, and that's equal to 0 because N minus 1 is 0. If N is equal to 2, we have 2 possible L values. L can be 0 and it can be 1. When N is equal to 3, we'll have three possible L values, 0, 1, and 2. Okay, and these are going to show us our different shapes. And in future slides, I'll show you what those shapes are. Okay, now let's go back to our periodic table. Okay, and the annotations for this are no longer here. So I'm going to go ahead before I do anything, and I'm going to come on down to our lanthanides and our actinides and show, okay, so we remember that potassium was level 5, right? No, sorry. I can't add. Potassium is level 4. Scandium was level 3. And see how lanthanum starts right here in the 57, okay? The first lanthanide is lanthanum, okay? These would be energy level 4 and energy level 5, okay? And then before we go on, these go with L values, okay? So these are the N values for this. And I know I'm doing this backwards now, but that's because I'll lose it when I move my periodic table here. These are associated with L values equal to, okay, and this is interesting, L values equal to, let's see, 1, 0, 1, 2, 3. Okay. And so this is an L value equal to 3. And it's called the F block. Okay. All right, now let's back up and, sorry, moving things around. All right, so now let's come back to what we're doing. And remember, I'm going to put our N values in here. 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Okay, and we had said L value went with shape. Okay, so first of all, what I'm going to do is I'm going to temporarily put helium right here. Okay, that's going to be a little bit easier to see. Okay, this is what is known as our S block. S block. And these elements go into L equal to 0. Okay, and then if we come over here, these here, not helium because we moved helium. So this block here in green is known as our P block. And it goes with L values equal to 1. And then here in our transition metals, you will see what's called our D block, and this goes with L values equal to 2. Okay. All right, and those are L. All right, now the next piece here is the magnetic quantum number. And the magnetic quantum number is M with a subscript L, and it'll be referred to often as M sub L. You'll hear me do that in various places. The M sub L, or the magnetic quantum number, describes the orientation of our orbital in space. So it's kind of like, is it on the x-axis or is it on the y-axis? And when we get to the pictures, I'll show you that in a minute. Now your m sub l values depend on your l values. And when m sub l goes from negative L to positive L. So what that means, for example, is that if L equals 2, then m sub L will equal negative 2, negative 1, 0, 1, and 2. And now finally, we've come to where we are. So if let's say that what we're looking at is we're looking at energy level 3 here, okay, and then L value 2 and M sub L values here. These are our 5 orbitals. And those 5 orbitals, each orbital can take 2 electrons, which brings us to our final quantum number, and that is our magnetic spin, or sometimes just known as the spin quantum number. And the spin quantum number describes the direction of spin. And it is m sub s. And for every m sub l value, it can be plus 1/2 or minus 1/2. Okay, sometimes this is also shown as spin up, spin down. Okay, now for each orbital, we can have 2 electrons. So if there are 5 orbitals, so m sub l negative 2, m sub l negative 1, each of these orbitals will have 2 electrons in it. Okay, and there's our 5 orbitals right here. And we can see that that means that our 5 orbitals would have 10 electrons. Now remember that this said L is equal to 2. Let's go ahead and go back to our periodic table. And you'll see right here where here we said that this was equal to L equals 2. It was our D block. Okay, and you'll notice that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons in here, which correspond to the 10 electrons from before. All right. Okay. So now, now you'll see that I'm back here in the slides, and that's just because I want to draw your attention to a few things. And that is here. All right, so first of all, this shows our shapes, okay? So you can see this S, okay? So in this, see this 2S, this is N equal to 2, and if we're in S, then it's L equal to 0. And 1S would be N equal to 1, and the S would be L equal to 0. Okay, so L equals 0 is an S orbital, and it looks like a sphere. And that you can kind of remember that because the L equals 0 only has one m sub l value, 0. And there's only one orientation for a sphere in space. No matter what you do with it, it is still going to look like a sphere. It's not going to change its shape. All right. All right, now we have our next one. Okay, and these are our p orbitals. Now we do not have, there are no p orbitals in n is equal to 1, because n is equal to 1 only has L equal to 0, and a p orbital is equal to L equal to 1. Okay, and that's our p orbital. And there's a p orbital for n is equal to 1, 2, n is equal to 3, 4, 5, 6, and so on. And if you remember with the m sub L values, this could be -1, 0, and +1. So here they are, -1, 0, and +1. And it shows the 3 orientations in space of what we're working on here. Okay, and then here are our d orbitals. Okay, so d orbitals, there are no d orbitals in n equals 1 or 2, and that's because L is equal to 2 for a d orbital. Now, if L is equal to 2, we saw before that m sub L would be -2, -1, 0, 1, and 2. We've got 5 of them, and you could put them here. You could say, okay, well, that's -2, -1, 0, 1, and 2. And they describe the shape and or the orientation in space of our d orbitals. And you could do that again for the f orbitals as well. Okay. Now, notice that we're talking about electrons. We started out talking about photons, and then we started talking about electrons. Okay, so we're going to do some more of this next week, or well, in the next video. But let's talk a little bit about, here we had a photon, right? And we talked about a photon as being light. So light, a photon is a particle of light. But we know that light is mostly wave-like. Okay, we know that it's like you can't pick up a light particle and see it, right? It's mostly, we talk about waves of light. We talk about wavelength. And so this would be our quantum mechanics, or quantum physics, if you will. Over here, let's say that we have a baseball, okay? And there's more about this in the slides. Over here, we'll have a baseball. A baseball is mostly particle-like, okay? It has a tiny, tiny bit of wave-like characteristics, but not really. I mean, if you pick up a baseball and get ready to throw a baseball or a football or anything that you're going to throw, you're not going to see the edges being like wave-like patterns. It's going to be this discrete thing, okay? This is where we're talking about more like classical mechanics or classical physics. That part in the center, and that's why we talk about them a lot in this chapter when we're talking about quantum, is the electron, okay? And the electron is partway between the two. Okay, and in part that's because it is so very, very small and it never stops moving. And that's why we talk not about exactly where an electron is, but where we're likely to find it, because we can't actually know those things. Okay, so let's talk about a couple of principles and where those are going to come in. And I have no idea where I am in here. All right. I can't find anything in my notes. Okay, so let's talk about the Heisenberg uncertainty principle. So somewhere in my notes, it'll talk about how the Heisenberg uncertainty principle says that we can't know the exact momentum of the electron. And what does that mean? Well, momentum or motion, in this case, is going to describe where we are, how fast we are traveling, and the direction in which we are going. And the reason that we talk about wave functions for electrons is, or orbitals that describe the probability of where we're likely to find it, is that it's impossible to actually know all of these things about the electron, okay? And that's our Heisenberg uncertainty principle. That's the end of part 1. Come back for part 2.